your seats, please. My name is Dr. Scott Chardiaski. I'm the chair of the Social Sciences Department. I'd like to thank all of you for attending this Kent Miller, Quinton Reeves honorary lecture series presentation. If you don't know, Kent Miller and Quinton Reeves were both longtime faculty members in the Social Sciences Department, and when we created this lecture series a couple of years ago, we decided we would name it in honor of them, not memorialize them, they're still around, but just to recognize them for their long terms of service. Now, this particular presentation, as you can see, called The Science Behind Global Climate Change, is a counter, if I may say, to Professor Jim Malot's discussion a few weeks ago on the very issue of climate change as well. So it seemed right that in a day where we want to make sure that all voices, all positions are heard, this seems to be an appropriate venue, and this is something that at college we encourage, the respectful and academic discourse on ideas, and including on ideas we might agree on. So today we are lucky to have Professor Dr. Allison Stamatis talk to us about this topic. Now, Dr. Stamatis is an associate professor here at Weatherford College. She's been teaching for 11 years at Weatherford College as well. She earned her Bachelor of Arts in Biology from Austin College, which was in Sherman, a Master of Science in Biology from the University of Texas in El Paso, and a Ph.D. in Environmental Science from the University of North Texas. So, with that, thank you.
Wonderful. Thank you guys for all being here. Well, I appreciate you being here. As you can hear from the kind of environmental science background, I have, this is a little bit of the, process with science. Scientists love to do research and find out information about the past and current and try and make predictions about what may be happening in the future. But sometimes with science, how many of you ever picked up a medical journal or a scientific journal and tried to digest one of those articles? Right? Kind of a little bit over our heads. Sometimes it's difficult to communicate that information to people who may not have that same kind of background. But always keep in mind that these same scientists, sometimes they're, we're self-professed nerds when it comes to that information. I just was at a conference last week where I heard someone make the joke, how do you tell the difference between an introverted scientist and an extroverted scientist? An introverted scientist will look at their shoes when they're talking to you, and an extroverted scientist will look at your shoes when they're talking to you. So bear with me. If there's anything, at any point, you have any questions about what's going on, and I'd love to open up some dialogue at the end if you have any questions. And then we have, various people from also science backgrounds here. If you're in one of my classes, thanks for being here. We know you're in here. But as we begin the talk, I want to kind of set the stage. It's the time of the semester where you're plagued with finals on the horizon. You've got so many projects being piled up from your various other, professors around campus. Or if you're on the faculty and staff side of things, you're grading all of those projects and those papers right now. So I want to transport you to a tropical paradise. So imagine yourself the Maldives Islands. These are in the Indian Ocean. You can see a little bit in the inset over here. And maybe you've seen, in social media or various news outlets, you've seen some of these kind of tropical getaways where you have this little hut that's out over the water. You walk over the water and you've got your own little tropical paradise. And so set the stage, you imagine you're walking out to this tropical paradise. However, the Maldives are in trouble. That whole island chain, they're right at sea level. You can see, just walking out onto the sea, literally from those huts. This picture on the left is Mali, the capital of the Maldives. And they have already been faced with rising ocean levels. There are a few islands in their chain that in fact have already had to be abandoned. So they have already become the first climate change refugees. They've had to abandon their homeland and move, probably to another one of those islands in the chain. But ultimately, all of the Maldives Islands are just barely above sea level. So they're going to be faced with this growing problem. What do we do with those growing sea levels? And in fact, some of the leaders of the country, they staged kind of for, to raise public awareness, they staged their first underwater cabinet meeting many years ago in the early 2000s, just to bring awareness to, this is, obviously it's a joke, but eventually this is going to be the reality that we're faced with. This whole area may be completely underwater one of these days. They've also seen other problems associated with that, not only physically not being able to inhabit it, but other problems with organisms that live in the area. You erosion of their beaches. The coral reefs around the islands have been devastated. So this may seem like, tropical getaway that may not happen in the near future, but you've heard about other stories more close to us. Yes, ma'am?
Would you speak up a little, please?
Sure. Maybe you've heard other stories about other coastal areas closer to home in the coastal United States. Maybe the coastal Gulf Coast of the U.S., along the Texas coast, where we've had rising ocean levels that have impacted some of the people that are there, and have an increased storm surge or intensity of that storm surge. But other areas, like when we're talking about our defense, for instance, how many of you knew that the largest naval station in the world, you probably could have guessed it was in the United States, but it's in Norfolk, Virginia. Anybody know that? Okay, maybe you've seen images, or maybe you've flown over or seen that area where we have hundreds of naval ships parked in this area. They have already been faced with rising ocean levels and increased storm surge intensity. So they've been faced with this problem and recognized back into the early 90s that this is a matter of national defense. This is something that if we don't proactively do something to react to it, maybe lessen that impact, and in the very least adapt to it, figure out how to adapt to those changing sea levels, then this may be something that is a problem going forward for not only for our economy, but also for our defense. And then other areas, like in southern Florida, Miami has trillions of dollars built up in infrastructure, not trillions, billions of dollars built up in infrastructure along that coast where it's right at sea level. And they continue to build there, but they're faced with a growing problem that now, about 6 or 7 times per year, they have water that rises up through this porous limestone and floods the streets. In fact, they've had, so you've probably seen video images, just on a normal sunny day, they're kayaking down the streets because they have rising sea level. And so now they have to just deal with it until it recedes, or find some way to pump that seawater back out to the ocean. So it's a growing problem that we've already realized, we've already come to deal with. But I want to talk about the science behind that. How did we get to this point? And then what do we see going forward in the future? What can we potentially do about it? So the first thing to kind of chat about is the title of this talk. Maybe you noticed it was Global Climate Change, and you've also heard maybe talks about global warming. Well, there is a discrete difference. Global warming is part of that, but it's not the entire picture. Global climate change has to do with changes to the temperature, such as average increases, and in some instances even decreases in temperature, but it also has to do with precipitation and changes to the ocean levels that I mentioned, where it's gone up on average almost 8 inches across the world. It also includes discussions about increased frequency of intense storms and increased intensity of those storms and storm surges. So that's why I prefer to use the term global climate change, because it implies that there's many other factors that are influencing our changes, not just the temperature. And then I also want to point out kind of the discrete difference between weather and climate. Weather is something that you have a little bit of predictability about, although if you look into this afternoon and try and predict what's going to happen with our weather, maybe you're checking your phones, sometimes we don't have the best predictability. But weather is the short-term pattern. That's what we think is going to happen in the next couple of hours, in the next day or two, and maybe projected out into a week. But when we talk about climate, that's a longer-term pattern. That's where we talk about our seasonal variability, where we think about what's winter going to be like the next year, the next 5 years. It's a longer-term pattern. And we'll talk about the things that influence those longer-term patterns and then can play some role, or do play a role, in our normal day-to-day weather. But let's look at the longer-term patterns first. So there are many factors that influence the climate, but the big 3 are the sun, and then the solar radiation that's coming from the sun, which we love because it heats up the earth, but it's kind of a blessing and a curse because it comes with UV radiation and all of those other impacts. The atmosphere. Without our atmosphere and our gases around us, we would be a very frozen planet. It would not be hospitable to life as we know it. So we have a lot of gases in our atmosphere that make this a very warm and balmy place to live. We have, when that solar radiation is coming down from the sun, it warms up the surface of the earth. It's absorbed by the water, by ice, by land, by many other surfaces. About 70% of that is absorbed, and the remaining 30% is reflected back into space. And then some of those atmospheric gases also help to reflect some of that back into the earth again. And in our oceans, because they cover about 71% of the surface of the Earth, they play a very large role as well, because the oceans have the ability to absorb a lot of that heat. It also influences our evaporation and precipitation patterns, the whole hydrologic cycle that you learned about back in grade school. So those are the three big things that influence our climate, in addition to some other factors, but those are the ones that we study the most with climate science. And you've no doubt heard about greenhouse gases and the greenhouse effect. Well, sometimes the greenhouse effect gets a bad rap. It has a negative connotation. But those greenhouse gases, in and of themselves, are what help to keep our Earth so warm and hospitable. In general, any gas that has 3 or more atoms that make up that molecule, those are going to be able to absorb heat. And so even something like water, you have H and then 2 O's, right? I mean, 2 H's and 1 O. So even that water molecule has 3 atoms in it. It has the ability, when it's in the air in that vaporous form, to be able to absorb heat. But water vapor, even though it is a greenhouse gas, we have not seen significant increases in that gas compared to some of our others. Some of the others that I've listed, carbon dioxide, 3 atoms there. Ozone, similar to oxygen, but it has a 3rd oxygen atom on it. And then nitrous oxide and methane, both come from various either combustion or the exhaust from various animals on either end, or also from fertilizer production. Various different things can contribute to those. And halocarbons. Most halocarbons are molecules that we produce. We've manufactured, like maybe you've heard of CFCs, the things that were used in propellants, like for aerosol cans. Those are our synthetic molecules that we have created. So those greenhouse gases rise up into the atmosphere and make that atmosphere kind of like a warm blanket. It holds in that heat that otherwise would be reflected back to space. So you know, when you're chilly at night, you put a blanket on yourself to keep you nice and warm. It holds in your body heat so it doesn't radiate away. But imagine if someone piled 2 blankets or 3 blankets on you at night. You'd start getting a little sweaty, right? Well, that's what we're seeing recently, is a rise in some, but not all, of these greenhouse gases. So what we're concerned with is not necessarily the greenhouse effect. Like I mentioned, the greenhouse effect is great. We appreciate it because that's what makes it a wonderful place for us to live. However, what we're focused on is the intensification of these greenhouse gases in the very recent future, or the very recent past, just in the past 200 to 250 years. So we refer to these as the human-generated, or if you want to sound really fancy and take a little bit of scientific lingo away from this, those are the anthropogenic reasons that we're having this intensification of this climate warming and this climate change. And we've been able to measure, either directly, and we'll talk about the indirect measurements, the carbon dioxide and some of these other gases that have been in our atmosphere leading up to our current history. So this is showing some of our top 3 gases in this data, this graph down below. We can see that it was held rather steady for the past couple hundred years, and then we see this very sharp increase. Does anybody happen to think of another graph that has a similar trend, where we see this, you know, maybe a little bit of an increase, but a sharp exponential increase? Maybe the human population, very good. So the human population also had a very similar trend, where it was kind of trucking along, getting a little bit bigger, and then right around the time of the Industrial Revolution, right around the late 1700s, early 1800s, when we started to be able to use fossil fuels for increased medication, sanitation services, more food production. Arguably, again, something that increased our, ability to survive on the Earth, increased our lifespan, life expectancy, all of those things, very good things. But it came with a cost. It came with the production of these increased greenhouse gases. So we've seen throughout the previous human history, we never saw a level above 300 parts per million. When you see that ppm on there, that means that that one molecule of gas compared to a million other molecules of gases in the atmosphere. So if we have 300 parts of carbon per million, that still seems like a small amount. But when we talk about that level steadily increasing, that's what we start to get concerned with. So just in our very recent history, it has gone above 400 parts per million, which had never been seen before, and it's now, just very recently, it's at about 411 parts per million. So that number is a significant figure that I hope you'll remember. There are many greenhouse gases that we could go through and discuss, but I want to spend a little bit more time talking about carbon. Because carbon, kind of like if you remember the water cycle, carbon is another one of those things that works in a cyclical process. It's a fundamental principle of physics and chemistry, something that we hold near and dear in science, that those particles, that matter, can't be created or destroyed. There's the same amount of carbon on the Earth as there was hundreds, if not millions and thousands of millions of years ago. So that carbon gets moved around. There's carbon in our bodies, we're carbon-based organisms. There's carbon in all the food that we eat. Whenever we breathe out, there's carbon dioxide, so we have carbon going in, carbon going out. And then we have photosynthetic organisms. This is your little brief science lesson, right? But hopefully it's sounding familiar. Those photosynthetic organisms are able to take carbon dioxide in. And then that's how they make sugars and proteins and fats that then we ingest, break those down through metabolic processes, and we breathe it out in that form of carbon dioxide. So the Earth kind of breathes carbon dioxide. It breathes it in, it breathes it out. And that's what you see with these green arrows. Photosynthesis brings in carbon dioxide, and then with all of those organisms that are respiring, like us and other animals, we have carbon dioxide that goes out. And there's this balance, we call that homeostasis. Those systems tend to remain in balance. The same thing with the ocean. The oceans can absorb carbon dioxide gas, it mixes together with the water, and they absorb oxygen gas as well, and other gases, but then they also give off carbon dioxide. The green arrows are representing the natural fluxes, that natural ability to breathe in carbon dioxide and give it off of the Earth, like the big perspective, big picture. The little, if you can see the thinner kind of gray arrows, the color's a little wonky on here. I just said wonky. But those green arrows are representing the anthropogenic, or the human-generated fluctuations of carbon. And we do have some human-generated fluctuations in carbon that are pulling more carbon in, and we have more that are giving off more carbon. But the net cumulative effect of where that carbon is going is that we have more entering our atmosphere than we've ever had before. And you're like, wait a minute, you just told me that there's the same amount of carbon that there always has been. How is there more going out than coming in? That's an imbalance. Well, we have a lot of carbon that's still stored underneath the ground in the form of fossil fuels. Those fossil fuels aren't dead dinosaurs like you may have thought about fossils, but they're mostly the remnants of decaying plants, decaying mosses, and marine organisms that were in our oceans millions of years ago. And under just the right environmental conditions, hundreds of millions of years ago, they got buried under sediment, and then with heat and decomposition, it turned those carbon-based organisms into those fossil fuels, which are highly combustible. And we were able to use for oil manufacturing, for vehicle transportation, burning coal for electricity generation, many different uses, again, which made our society what it is today, was able to lead us to be the United States and other countries, lead us through our industrial revolutions. But that net accumulation is what we're concerned with. And if you're like, well, aren't plants the answer? Plants are able to take in more carbon dioxide if we have more going out. Yes, plants can be the answer. But unfortunately, do we have more forests today than we ever did before?
Less.
We have less. We have fewer forests than we ever did before for various reasons, most of which is deforestation for either agriculture or human habitation. So our natural buffering capability for being able to take in that carbon dioxide has been diminished. So that's where we've kind of gotten into trouble. We're pulling out this source. Basically, in science, we refer to it as different reservoirs of carbon. We have a reservoir of carbon in the ground in the form of fossil fuels. It took it millions of years to get there, and we're extracting it and burning it at a faster rate than we're able to have organisms that capture that carbon again. So it's just a matter of where the reservoir is. Right now, the bigger reservoir is building up in our atmosphere, which is what gets us to the problem with throwing those greenhouse gases out of whack. It's like putting on a second and a third blanket at night, keeping you a little bit too toasty. So those greenhouse gases are a big factor in what determine our atmosphere and our temperature, and also our different climate patterns. But we also have some other things that can influence our temperature. We have different aerosols, not just the gases, but different just microscopic vapors or microscopic droplets of material. we have like soot, for instance. Soot is what we call black carbon aerosols. And you can imagine, like when you're wearing darker clothes, it's a little warmer outside, or you feel warmer, because that darker color absorbs more of that sunlight, versus a lighter color reflects more of that sunlight. It's the same thing when we have these particles in our atmosphere. Those black carbon aerosols cause a little bit more warming because they absorb more of that heat coming down from the sun. But we have other aerosols called sulfate aerosols, and those sulfate aerosols are a much lighter color, and they reflect back a lot of that sunlight. So those sulfate aerosols actually exert a cooling effect. So that's why, again, we try not to say just global warming, because there's also global cooling that's occurring as we have more sulfate aerosols, such as with combustion of fuels, like jet fuels. When you see those jet trails up in the air, there are sulfate aerosols that are present there that actually cause a cooling trend. But what's the net cumulative effect? We've looked at the cumulative effect of the carbon accumulating in the atmosphere, but let's put all of these things together, and I can't cover all the ground of all of these things, but scientists have gone through and said, okay, what's the cumulative effect of these greenhouse gases, other substances, all of the anthropogenic, the human-generated things that can potentially warm or cool our atmosphere. And they look at that, whether there's a net gain or a net loss in or cooling versus warming. It's what we call radiative forcing. And with radiative forcing, the units that we use are watts per square meter. So you know what watts are. That's the unit like when you have a light bulb and you're trying to find the appropriate wattage of that bulb. That's the measurement of that intensity of the heat. Per square meter is just looking at an amount of land, how much heat is distributed on that land. So everything that's to the right of this 0 line, that has a net positive warming force. And then everything to the left of that line, and they color-coded it in a red versus blue. Red is the warming, and blue is the cooling effect. These are just the anthropogenic things. These are just the things that humans can contribute to. We're not even talking about the solar radiation, oceans, things along those lines. The net effect, when we add together those various greenhouse gases and the aerosols, is 2.3 watts per square meter. And you're like, is that a big number or a small number? Well, 2.3 watts per square meter is about the equivalent if you took 200 regular incandescent bulbs, which we don't use too much anymore anyways, and you distributed that heat over about the size of a football field. So you're like, that's not super warm, right? And it's not. 2.3 watts per meter is not incredibly hot. It's not toasty where you're going to start sweating right away. However, the cumulative effect of when we see that again and again is what we're worried about, that it already is a positive number. If we didn't have these anthropogenic changes, then we would hope that that number would be 0, that there would be neither a positive effect or a negative effect. So that's the concern, is that it's just positive, period. But what about the natural cycles? If we say, well, okay, there are natural warming periods and cooling periods in our climate. And in fact, we can go back and look at many of those very same periods in our past. Yes, there are absolutely natural cycles that fluctuate and can vary our climate conditions. So I'll address a couple of those things. One of those is that the Earth varies, and you know that the Earth tilts on its axis, right? But it wobbles a little bit whenever it's tilted on its axis. And even that degree of tilt can fluctuate by about 3 degrees. And then the Earth, because of that wobble and because of that tilt, also varies in its orbit around the sun. So you can see in the picture down below with that variation, there may be some time periods when the Earth is much closer to the sun, leading to more direct radiation, which leads to more warming. And you're like, well, yeah, I can see how any of those fluctuations would definitely put us into either a warming period or a cooling period. But when we talk about the timeline for how long it takes to go through one of those complete cycles, for the axial wobble, it's about a 20,000 year time period to go through that full cycle. For the variation of the tilt, it's about a 41,000 year cycle. And for the variation of that orbit, that's about a 100,000 year cycle that it takes to experience those major changes. So again, what we're looking at are the changes that we've been able to see that have just increasingly gone up in our last couple of 100 years. Not anything that we would expect to be able to see on this, thousands, if not hundreds of thousands of year time scale. Other things that can influence our climate dramatically is the variation in solar output. There are times when the sun has more solar flares, there's more radiation that reaches our Earth, and of course that causes warming. And there are times when the sun is a little bit more quiet, when it has fewer solar flares, and that can lead to dramatic cooling. But again, with this radiative forcing idea, whether the positive effect or there's a negative cooling effect, there is a positive effect of having more solar output, but scientists have only assigned it a value of about 0.5 watts per square meter. So small relative to those other anthropogenic changes that have increased. You're also familiar with ocean currents, that's a thing, right? That the oceans are not just stagnant, but there are these deep sea currents that can transport warm water and cool water to various parts of the Earth. So most of that warm water is occurring at the equator, where we have more solar radiation. It warms up those ocean waters, and then they start to circulate. Those warmer ocean waters are less dense than the kind of cold, sluggish water. It's more dense down below. So these warmer ocean currents tend to start moving north from the poles and south, and then they can carry with it that warm water. So for instance, most European countries on that Western European side, it's hypothesized that it would be a much cooler place if we didn't have this warm water current moving past it. But it's also possible that those currents can be disrupted. For instance, they've already seen a slowing of this current that goes past Europe, carrying that warm water. It has been slowed down somewhat by melting of the ice sheets that are in Greenland. And when we have those melting, that fresh water, the fresh water enters that ocean water, and it changes the density of the water, and it can cause it to slow down. So we're already, yes, my point was, yes, that can impact the local climate to an entire continent, but it's something that we may see the reverse trend right now. That's not enough to show us the short time span trends that we're seeing with anthropogenic climate change. And then you're also familiar, if you remember being in one of those El Nino or La Nina years, where sometimes you have maybe in a dry and normally arid area, but you have copious amounts of rain. Or you're used to having plenty of rain and you enter a long dry spell, the drought period. We're all familiar with those El Nino and La Nina cycles, but those are periodic fluctuations that don't lead to a longer-term climate pattern or climate change. So those are all influenced by changes to surface sea temperature, also changes in atmospheric pressure, and it's mostly having to do with circulation patterns in the Pacific Ocean. So we know that these trends are there. These are patterns that can alter our climate. But this multi-year variation or just local climate changes is not enough to describe what the changes that we're already seeing with our climate worldwide. So this is where we get into the measurements. How do we know this stuff? How do we know how much carbon dioxide has changed over the years? How more is entering the atmosphere? We have various indirect and also direct indicators of what has been occurring. So we've been able to take what we call proxy information. A proxy is kind of like a stand-in. And we take this proxy data from mostly ice sheets. There are ice sheets where they drill these cores way down, and they can get, it's kind of like the tree rings. You've probably, imagined a tree ring before or seen it, where you see these little layers in the tree indicating, if there's a thicker band, it's when there was more precipitation. Thin band, when there was less precipitation, couldn't grow as much. We see the same thing in these ice cores, taken from ice sheets, also from glaciers, and also some sea ice. And we've been able to find that inside of that ice, like let's say you just put some water in an ice cube tray in your freezer, turns into ice. Well, there are little air bubbles that get trapped in that ice cube. And those air bubbles capture all of the gas that was in the atmosphere at that time. And then with a very fine needle, you can extract those gases and know exactly what the atmospheric gases were like at that time. And so by drilling these ice cores way down into these glaciers and ice sheets, they've been able to find the gas amounts that were in the atmosphere at that time from hundreds of thousands of years ago. And they've correlated this data. This is a study that's been going on for decades. They've correlated this data with different ice sheets in different parts of the world. So that's how we can get carbon dioxide, nitrous oxide, and also methane data dating back many, many years ago. We also have some indicators that come from some other less kind of traditional sources. We do look to tree rings, and we can see years where there was more precipitation, less precipitation, years of fire, because we have some trees that live for thousands of years, some of them 5,000 or 6,000 years in age. So we can trace back what our climate might have been like many, many years ago. We also can drill sediment cores, the same thing, it's like a vertical core that you take, but of the sediments beneath an old lake. And we can look at maybe pollen samples, various organisms, and also gases that were trapped at the time that that sediment layer formed. And then another one that's interesting to me, just because it's kind of quirky, pack rats. Maybe you've used that expression a time or two with someone you know, or maybe someone's used it on you, but a pack rat is a real organism, and they do like to store stuff. They store things and they kind of hoard them in like a little cave or sometimes even under a bush, and they're very territorial. They pee on their stuff. And then that urine kind of hardens, and that becomes theirs. Nobody else is going to bother it until that pack rat dies. And then another pack rat is like, it's mine, it's all mine. And they take over that middens, and it becomes theirs. Then they pile up some more of their stuff in that middens, and then another pack rat does the same. They have some pack rat middens that are tens of thousands of years old that have collected just stuff. I mean, they're huge. They have to take samples going all the way down to these pack rat middens. And because these pack rats collected the plants that were around at the time, that's a record of what our climate was like in our past. So that's another what we call proxy indicator. It's an indirect measurement of what our climate was like in the past. So next time somebody calls you a pack rat or something, say, oh no, at least I don't pee on my stuff, right? So this is just, the picture down at the bottom left is showing if you were able to look microscopically at those little tiny pores that are trapped in those ice bubbles. And then it shows some of the data to the right with the fluctuation in carbon dioxide dating back to about 800,000 years ago. And also in the blue, we have methane that was also trapped in some of those ice bubbles. And then we've also been able to see, if you notice the fluctuation, they tend to correspond pretty closely with one another. When we see an increase in one of those gases, we see an increase in the temperature. When one of those gases decreases, we see a decrease in that temperature. So there's a pretty tight correlation between increases in those greenhouse gases and increases in the temperature. And again, this is where the writing's on the wall. If we're concerned about, and this has never been, remember that magic number above 300 parts per million? It hadn't been above that in the past 800,000 years. And that's why we're so concerned now, is that currently today, and this graph is a little bit old, it was from a 2008 publication, that was at 406 then, and now currently it's above 400, it's at 411 or so. So this is where the growing concern comes in. But if you're like, well, that's indirect data, how much significance can we attribute to that? Convince me with some direct data. Well, there was a scientist in the mid-1950s that first was able to devise an hourly capture system to trap carbon dioxide that was actually in the air, right then and there. And then by 1958, he installed the first ever, and it's the longest continuous monitoring station for carbon dioxide. His name is Charles Keeling, and he set it up very intentionally in Mauna Loa, Hawaii. And you're like, oh, I know why he did it in Hawaii, because it's Hawaii, right? But take a look at this. This is actually the Mauna Loa Observatory. I don't know if you can pick it out from the picture, but it's a rather deserted place. It's not the tropical, visions of Hawaii that you imagine. That was intentional. This was in an old lava field where there was a long dormant volcano, but the vegetation hadn't grown back yet, and not many people lived there. That's why he set up the observatory there, because he didn't want the fluctuations in. If there's a lot of plant matter, what do they do with carbon dioxide? Yep, they suck in the carbon dioxide. And if there's a lot of humans living there, what do they do with carbon dioxide? They're breathing it out, right? So he wanted it to be a little bit more free from some of those influences. So he set up this monitoring station, and it's been continuously running ever since then. And now it's operated by NOAA, the National Oceanic. But this is showing the details. I don't know if you can make this out. You can see this red line that's kind of like a zigzag. It goes up and down, and up and down. But then you take a big step back, and you can see the big picture trend. And that's what the black line is. The black line is showing the annual average in carbon dioxide. The reason that there's that up and down and up and down What happens with trees in the winter? How much photosynthesis are they doing? Not that much, right? Not all, but a lot of trees lose their leaves in the winter. So photosynthesis slows down. So what do you think happens with atmospheric carbon dioxide during those winter months? It's going to go up. And during the spring and summer months, when the trees have leafed back out again, what are they doing with that carbon dioxide? They're taking it back in. So when you see this line that's up and down, to me, it's a beautiful picture. It's almost like you're seeing the planet breathing. You're seeing the planet take up that carbon dioxide and breathe it back out. Take it in and breathe it back out. So that general trend, however, that's the wake-up call. Because when he first started measuring this, it was at 315 parts per million in 1958, already above, and at that time they didn't have the ice core data, but it's already above what we had seen, at least now, in our past history for the Earth. And now above 400, closer to 410 or 411 parts per billion. So with this information, with the indirect evidence, with the direct evidence that we've gathered, and also knowing more and more about our atmospheric conditions and being able to monitor them, we can put that data together and we can do what we call climate modeling. Climate modeling is where they input all this information, and it's not dramatically different from what they do to try and model to figure out what the next day's weather is going to be like. It's kind of a prediction of what the weather is going to be like in the very short time periods coming up in the next few hours, in the next couple of days. But we're talking about a larger picture, a larger trend by looking at the climate. So with these climate models, at first when they devised them, they weren't very accurate. They were trying to input so many different variables that influence the climate, right? We just mentioned a few of them, and your head is already swimming. So they were trying to input this information, but then the models started getting better and better because they could test the models and see how they held up to what actually happened. So the models now, that they've been around for 20 years or so, have gotten very good. And I had the fortune of being able, I was at a conference last week in St. Louis, where there were science teachers abounding from all across the United States. I also had the fortune of being able to hear the astronaut Scott Kelly, the one who spent the most time in space ever. He was our keynote speaker. But I was able to meet with a NASA scientist, which was just cool. You know, I'm talking to a NASA scientist, and he has worked to develop, he works at Columbia University, is where he's stationed, but he has developed a climate model called EasyGCM. The GCM is for Global Climate Model. And he gave me access to it because that's his intention. He's like, these climate models shouldn't just be for the climate scientists, for them to say, this is what we've developed, you should trust what we say. But he wants students to also be able to understand what goes into the climate model. And so we can understand the trends, and as time goes on, how they get more and more accurate. So I do have fortunate access to EasyGCM now to be able to model any of this for you if you'd like to kind of see what the trends are. And then taking all of this information together, we already have seen the writing on the wall for quite some time. The United Nations in 1988 put together a committee called the Intergovernmental Panel on Climate Change, or the IPCC. They wanted scientists from around the world to be able to inform other scientists about what they're seeing. Trends in temperature, atmospheric gases, trends even in organisms, in human health, if we're seeing differences in human health diseases and impacts from sea level rise. Many different scientists, thousands literally from across the world, have given input to the IPCC. And the IPCC, periodically, it's not a standardized every 5 or 6 years, but periodically they come out with an assessment report where all of these scientists get together, they pull their information into one report that can be used to inform us, and that can also be used to inform political decisions, like any policies that need to be made. And so they're trying to pool the information together just so we can all know more about it. In the current report that we're on right now, in 2014, they finalized their 5th assessment report. So you may have noticed underneath some of my data tables that I presented, if it said IPCC, and I had some of it from the 5th assessment report, and some of my graphics were from the 4th assessment report. But that's where I've gotten my data, because it's scientists that have spent their lives working on this information, and it's not just one scientist saying, this is what I think. It's hundreds of, if not thousands of scientists. Actually, in the 5th assessment report, there were 831 scientists that contributed to the data that was presented there. So talk about your peer review process and having to get through a very rigorous gauntlet of information. So what we're going to see in the kind of second part of this talk is, and kind of we're on the downhill slope, don't worry, that we'll talk about some of the impacts that we're seeing. And I don't like, a lot of you know me, I don't like to be kind of the doom and gloom person, like, oh no, we're going to hell in a handbasket, hurry, run, ocean levels are rising, we got to run away from it. I'm not the kind of doom or gloom person. I'm the eternal optimist. I like to look at this and say, okay, we're seeing some changes, what can we do about it? What are some solutions? So that's ultimately what we'll arrive at the end of this. You have already seen, and we've talked about, flooding in the coastal United States. Many of you may know or personally experience the impacts from our recent hurricanes that we had, like Hurricane Harvey, etc. in 2017. We've also seen prolonged droughts, unprecedented wildfires in California, and just long periods of heat waves and even cold snaps. Any one individual weather event, we can't unequivocally say that was from climate change. Or here's the kicker too, when there's a cold snap or a prolonged snowpocalypse or something in the Northeast, and they say, oh, where's the global warming now? We can't attribute one event to global climate change. However, we can say that the intensity of those events, the frequency of those events, that has been intensified by our anthropogenic changes. Yes, sir?
I recently watched the special Weather Channel where it talked about the top 10 worst weather years, and what I observed was, perhaps in my lifetime, 5, 6 out of 10 events back to occurred in my lifetime. Very recent. That really opened up.
Right. We would expect, that the law of averages, if nothing else was impacting it, that it would be spread out over a wide time period. But yes, that's exactly what we're seeing, is that the most intense events have happened in a very short time period. So a few of those changes, we've mentioned the warming before. Temperatures do continue to rise. We've seen globally in the past 100 years that temperatures have risen just on average about 2 degrees Fahrenheit. I have Celsius up here as well, but most of our brains work a little better with Fahrenheit. And just in the United States alone, this is showing in the past 2 decades, relative to the first half of the 19th century, or the 1900s, that in just these past 2 decades, the temperatures have risen on average more than a full degrees Fahrenheit. So that's and we've probably noticed this. We've noticed it even more so on the western half of the United States, and even in those northern regions. But that's what we've already seen. What about with those climate models? What are the predictions of where we might be going? This is a prediction of where the temperatures would increase based upon many climate models that have informed this. And this is again from the IPCC 5th Assessment Report at the end of the 21st century. So by 2100, what might the trend be? And we do see that those temperatures continue to rise, that on average, temperatures would increase, and especially our polar regions, especially the Arctic, would have the most warming. And the reason that we see less warming in the larger ocean areas is because, remember, oceans have the ability to absorb that heat. They can buffer it a little bit better than the land can. But those Arctic regions, again, are going to be by far the most severe as far as their intense warming.
Why the Arctic?
Just because of the way that the atmospheric patterns, the global patterns, especially with the water circulation, those thermohaline currents also help to drive a lot of that warming. So, great question. Another thing that we're seeing is differences in precipitation. Notice it's not across the board, there's flooding everywhere, or there's drought everywhere. We see that, yes, there are some areas that will face more, and this again is a prediction of what we would see toward the end of the 21st century, that we do have more precipitation in those areas where we see more intense warming. Because some of those areas, the warmer the atmosphere is, it can hold more water vapor. And so we tend to see about a 2% increase worldwide over the past, in that next 100 years, or toward the end of the 21st century. But we do have some areas that would be stricken with even more drought, like some of our areas like Saharan Africa, that would have even more pronounced drought than what they do today. So we see differences, but major prediction or major trends in what might happen as far as increased precipitation in some areas, but decreases in other areas. Another thing that we've already kind of alluded to is this extreme weather patterns that we're seeing with more intense storms, more intense wildfires. This is going to become the new normal. And you've probably even heard that phraseology before, right? Like, just get used to it, that's our new normal. It shouldn't have to be, right? We shouldn't have to reset and say, okay, that's just the new way we're going to operate. But we'll talk about how we can potentially deal with that. And then just kind of some more discussion down here about, like, our three major hurricanes, there were even more than that. But Harvey, Irma, and Maria all occurred within that same calendar year, a very short time span of one another. They are 3 of the 5 costliest hurricanes in United States history, dealing with inflation taken into account as well. And we've seen, doubling of insurance losses worldwide because of the losses that we're faced with from some of those extreme storms. We're already seeing that we're having more melting ice, especially in our Arctic polar ice caps and in many glaciers that are in the northern and southern hemispheres. So with this particular glacier, you can see we have evidence dating back to the early 1900s of the extent of how far these glaciers reach. And glaciers they melt in the spring and summer months, and then they grow in the winter months, and then they shrink and they grow. And they have this natural cycle. That's how you get how you can find those core samples. You find little rings in them, and they shrink and they grow. But the general trend that we've seen is that they're just not growing back after they've shrunk in those winter months. And so we're seeing many of these glaciers almost completely disappear. Some of them have. When those glaciers no longer are there to melt in the spring and summer months, that's supplying water to millions of people. That's supplying fresh drinking water that flows into rivers, lakes, and then fills up reservoirs. When we look over here to this top left picture, this is kind of looking down on top of the globe. This is looking down on the North Pole, on the Arctic. And this is showing the extent of the polar ice caps in the largest extent. This is in 2000, showing out to the kind of reddish area. And then you can see in 2002, it's shrunk, and this is based upon satellite data. And then it continues to shrink, and there are even predictions made. The yellow and white areas are predicting how much that polar ice cap might shrink. And if you think, well, okay, big deal, what if the polar ice cap shrinks? Well, that's all fresh water. That fresh water is what's entering our oceans and potentially disrupting those circulatory patterns. It also potentially opens up new passageways for travel, for ship travel from various countries, which you think, well, that's a good thing, right? Well, not when those ships also open up more exploratory drilling and mineral extraction in some arguably very fragile ecosystems and habitats. It also, there's this positive feedback cycle that occurs. We talked about dark surfaces versus light surfaces already, right? When you have a lighter colored surface, it reflects more sunlight, leading to more cooling. Well, when this ice melts, what's the color difference if it was ice that was over the ocean or even on land? That surface that's no longer covered with ice is a darker surface, like it's ocean water or if it's land. So it absorbs more heat. So then the more heat it absorbs, the more it causes that ice to melt. And the more ice melts, the darker the surface and the more heat it absorbs. So it begins this positive feedback cycle of more and more melting of those surfaces and more warming, more melting, more warming, more melting over and over again. So we're seeing it actually speed up as the polar ice caps have already shrunk. So that's one aspect that can also impact the oceans. Another one is that we said, the oceans have this ability to buffer that carbon dioxide in the atmosphere, but there's this simple little chemical reaction that occurs whenever carbon dioxide mixes with water. I have a soda stream at home, like where I sometimes make my own soft drinks or sparkling water, and all it does is it's injecting carbon dioxide into water to make it sparkling and fizzy. And when you do that, it makes that water more acidic. It makes it more acidic because when CO2 combines with water, it makes carbonic acid. And carbonic acid, it's got it in its name, right? It's acidic. It has a lower pH. And so that increased concentration of CO2 building up in the ocean water has made it more acidic. It is already decreased by about 1/10 of a pH unit. And you're like, 1/10 of a pH unit? Are you kidding me? Well, the pH scale is a logarithmic scale. So when you look at that decrease by just 1/10, that's about a 26% increase in acidity because it's lower on the pH scale. Now, the organisms that have to live there, that makes it difficult when that's their habitat, especially corals. They live in already very sensitive conditions, but They have to have just the right pH, just the right temperature, and just the right amount of solar activity. So the acidification of those oceans is leading to more and more coral bleaching, which you've probably already heard stories about how the Great Barrier Reef that was recently found in the past few years, that it has been even more devastated than what we previously
I think
predicted.
you said 50% loss.
50% loss, that's a little depressing, but we'll hopefully get to some solutions, or at least keep it from getting even worse. What about fuzzy little critters? Maybe you've got a warm spot, maybe you can't see critters in the ocean, but how about this cute little guy over here to the right? This is a pika. Pikas kind of look like a rabbit with shorter ears, and they live in very mountainous areas. They prefer really cold temperatures. We've already seen that pikas are having to shift their habitat farther and farther north, and eventually the mountain's just not tall enough to get, to a colder and colder climate. So we're already seeing pikas, and we have these in the United States, we're already seeing pikas disappearing from their habitats. This is another bird where we can see that it's called a purple finch. Its range, where it was traditionally found, has already shifted much farther north because it has a very narrow range of ideal temperatures where it likes to live. And if you're like, okay, well this, cute little critter over here, but it doesn't directly impact me, how about any other organisms that directly impact you that may be shifting their range? Quick quiz, what's the deadliest animal in the world? What kills more humans than any other? Right?
Mosquitoes.
Mosquitoes. Is that what you thought? You were thinking black mamba or some kind of like lion. Yeah, mosquitoes are the deadliest animal in the world because they kill more humans because of the diseases that they transmit. So we're talking potential health hazards when we have mosquitoes that are being able to extend their range farther and farther north into warmer and warmer climates. 5 years ago, did you know what Zika virus was? You didn't. It did not exist here. West Nile virus is just kind of a thing now, right? Like you expect to hear about some West Nile virus cases every summer. But 20 years ago, or even 15 years ago, West Nile virus wasn't a thing in the United States. So we are already seeing increases in the disease because their vectors, the mosquitoes, are being able to move farther and farther north as the climate is getting warmer in those areas. And then other problems, when we talk about flooding. Flooding, yes, can directly impact humans because that's where you live, but it also can flood wastewater treatment plants and septic facilities, and that's just a yuck I don't want to necessarily have to deal with, but we're already faced with that problem. We've already seen this in Florida. They are having to deal with where our sanitation services, and we got to protect it. We have to double down and make sure that that's not leaking out when we have all of this ocean water. Not even to mention the corrosion that they're faced with as the seawater is inundating their coastline. So what do we do about it? Well, a couple of things. Number one, we have to address the trend of the currently increasing greenhouse gases. So there are many different steps that we can do as a state, as a city, as a nation, and as a global population to address these problems, to try and lessen the effects of the things that we've already set into motion. So one of the big picture things that we can do is what I call mitigation. How can we lessen the effect of what we've already set into motion? We're not going to stop using greenhouse gases all of a sudden. We're not going to stop air transportation and driving our vehicles and trucks, all of those things. But how can we lessen the impact of each of those? So there's a multi-pronged approach. Unfortunately, if you were waiting around to hear what's my silver bullet, what's the big solution that we can do, there's not necessarily one. It has to be many different things that come together. And when you think about it, is what's that one solution for weight loss? There's that one thing, right, that you can do to lose weight? No, there's not. It's always a multi-pronged approach, right? What's that one thing that you can do to get an A in class? It's a multi-pronged approach. You talk to your professor, study, come to class, all of those things, right? It is no different with climate change. It's a multi-pronged approach to lessen or mitigate the impacts that we have. And then the other side of that coin is that unfortunately we have to adapt to the changes that are already taking place. Adaptation. Miami is already doing this. They have to, otherwise they got to move. This is showing some of the pump system, the very elaborate network that they have for pumping out that salt water and getting it back out to the ocean. It's kind of just this vicious cycle, but they've got to do something, otherwise they're swimming to work every day or kayaking to work. So ultimately, it's not one or the other. Do we pick mitigation or adaptation? It's both. Both of those have to work together to be able to lessen these impacts going forward. I like to think about what's going to happen to my kiddos and their next generation, the next generation after that. I want to try and take care of this place now so it's a better place for everybody after me. So that's where I task you guys. I have one more slide before I got to my big impact. I want to talk about the Paris Climate Accord. The Paris Climate Accord was where multiple nations come together. It was kind of in direct response to what happened earlier with the Kyoto Protocol. The United States had signed that but never ratified it. But with the Paris Climate Accord, the United States did sign it and ratified it, as did 185 other nations. 196 actually signed it, and 185 came back and ratified it and said, we are going to work together to do both the adaptation and the mitigation, to lessen all of these things that we're already seeing. And so those pledges, all of these countries in the world said, yes, we'll all do our part, especially if we're a nation that produces a majority of these greenhouse gases, which we are in the United States. So here's where I was about to go before I jumped the gun. The most influential factor, I believe, and a lot of scientists will also agree, may be the collective actions of just millions of everyday people like us. You may not consider yourself to be a scientist. You may want to be very far from that. But your individual actions can add up. And I think that's what it's going to have to take to be able to do this, to do all of those actions together. So I want to task you with just thinking about something that you can do. And actually, you've already done one thing. You maybe educated yourself a little bit more about that. And then you can educate other people. That's why I do what I do, is because I believe education is a really powerful tool for increasing other people's knowledge. So you do the same thing. You teach somebody else about it, and then somebody else and somebody else. And teach the kiddos too, because they'll know about it. All right, that's it. Thank you guys. Any questions? Or if you have to go to another class.
You have to leave, now's the time. Otherwise, if you have any questions, please raise your hand and I'll throw this at you, which is a microphone. So.
Don't ask me to throw it. I noticed Nick, you didn't show up.
So, with the Paris Accord, you didn't get specifics on actually what they do to mitigate?
Right, to mitigate. That's a great question.
And also with that, can you address the fact of didn't our president take us out of it?
That is correct. So his question was, what are the actual steps that we will take to do? That's left to each country. We're given this overall goal to try and decrease, let me go back to that slide, to try and limit global warming to 2 degrees Celsius. So how each individual country gets there is up to that country. So, for instance, China has made this goal, because China has very large deposits of coal, that was a really cheap, easy fuel source for them to use to drive their industrial revolution. But that coal came at a cost, as far as air pollution and increased CO2 emissions. So China has they have governmental mandates now where they're going in and shutting down coal-powered electrical generation plants. And so each individual country, and they are actually doing it, they are shut down even just small-time coal-powered kilns.
Right now they're doing it, so I think they're actually trying to increase it again to mitigate the effects of their economy.
Right. And that's, when we're talking about, how do we want our government to do the same thing, to come in and say, shut down that coal-powered electrical generation plant? We don't necessarily want every government to follow China's suit on telling us exactly what to do, but each country has their own pathway forward on just trying not to get past that 2 degrees Celsius warming trend. So each country has their own method. I kind of listed a few of them here. In the United States, their big plan was to take most of those coal-fired generation plants and convert them to gas-powered. And so it wasn't completely getting rid of CO2 emissions, but it was dramatically decreasing them and decreasing other side effects, other aerosols and sulfate, nitrous oxide, that kind of thing. And then you also asked the question about, did the United States withdraw from the Paris Climate Accord? And we did. In 2017, as soon as it was, because the accord only went into full effect in 2016, we had to wait for it to be into effect 1 year, and then President Trump said that the United States is going to withdraw from the Paris Climate Accord. However, there is, because it was a binding agreement since the U.S. signed it and ratified it, where there's a 3-year time period before, like from the time that it was instigated, before we can fully withdraw. So by I think it's June of 2020 is when we officially be out of the climate accord. But that doesn't mean that like there's a coalition of mayors and governors. There's like a governor's panel on climate change, where those governors meet together and they say, just because the United States does not, is withdrawing from this climate accord, doesn't mean that we can't try and meet those same goals. So, a little bit of
Technically on our federal system, it's going to be based off a state-based approach where the federal government will set the standard, and the law that will be the state having their own agencies in charge to actually monitor and comply with the situation that the federal government does. And that's the best way to do it because that's the way our Constitution designed it to be.
Thank you, Brandon.
Other questions besides Brandon? Do you have another question?
I do. So, I know you brought up IPCC. I was in the understanding that there are many thousands of scientists who don't necessarily agree on man-made global warming, and they say that that what's causing climate change and global warming is based off natural effect, sometimes either by sunspots on the sun or the fact that we've never had a stable climate. So with that said, what would you say in regards to them, and then also the fact that the ones who do believe in man-made global warming who are pushing policies, I mean, it's a possibility that they're pushing policies that may draw people into poverty out in the street, and so can you just address that?
Sure. That's the talk that we had a couple of weeks ago that Jim Malott was able to present on, kind of showing the other side of things, that there are natural trends, and that's the only thing that's dictating the fluctuations in our climate. And that's why I also tried to present, a significant portion of my talk to show that, yes, there are absolutely natural trends, like the solar output fluctuations. There are fluctuations, but the overall radiative forcing just from those solar flares was only 0.5 watts per square meter. So, but even faced with that evidence, again, you're right that we do have scientists that still ascribe to that there aren't those anthropogenic causes that are increasing the trends that we're seeing now. The trends, and certainly Mr. Malott can address that as well, but what we're seeing now is that, and I don't know, you mentioned thousands of scientists, I don't know the exact number on the ones who would agree that we're not seeing these anthropogenic changes.
Less than 12,000. Whereas
What's that?
32,000 meteorologists, climatologists say no.
Okay.
And they know what they're talking about.
And so, but tell me, so for the benefit of our audience too, if they weren't able to be here several weeks ago when we did the talk. So when we're faced with, so is there any denial of like the increases in carbon dioxide?
No.
It's an increase in greenhouse
Carbon dioxide is
gases.
increasing, thank you.
And does carbon dioxide increase the temperature on the Earth?
No.
Carbon dioxide does
Does
not.
not.
It's not a greenhouse gas?
It slows down the temperature of the Earth freezing for a second, it goes right out to space.
Okay.
That's part of that 80%.
We'll have to agree to disagree on that.
30% you talked about. That's reflected back to space.
Mr. Seeger, did you have anything? You're
I'm
done.
trying to keep my pie hole shut.
I would say that it's based off the adaptation of the human body and how much we can actually adapt and how much of the temperature we can actually adapt. But studies, I think, have shown that the human body is best suited up to 70 to 90 degrees, which is basically from originally we were from the Africa, Sahara, which makes a lot of sense. But when those temperatures can, whether it's ever weather caused or just natural cause, it's going to make a lot of these conditions unlivable. I know that there's a saying that there's a lot of people that live up the north in the Sahara Desert, but you got to think of the number of elderly or disabled people or children that actually get affected by the increase in heat strokes or flooding.
Unfortunately, a lot of my science department colleagues are in the Bronx right now. Well, hopefully, if you have questions about it too, I question science all the time. Go to the evidence, find the evidence, and ask questions of it. Yes, sir.
So, I don't know if this is more of a question or a statement, but, so I'm not a scientist, and I don't have a degree in science at all, but the reason why I'm skeptical about the belief in man-made global warming is, for one, I see as the side who believes in man-made global warming that it's a lot more political with them, and when I see a lot of these people on TV, either they make statements like 99% of scientists agree that man's causing global warming, when in fact there's many scientists who I see that their voice is not being heard. And then when you do see it on the media and in politics, that they're always showing one side. And I just want to ask you, I guess,
address that.
do you think that one side is being pushed more than the other side, and there's not having that fair debate in the public?
A couple things. I'll get to it, Brandon, then I'll let you finish. So, a couple things when it comes to the language that's used when you talk about 99% of scientists. If you look to the IPCC report, they don't use the language of 99% of scientists, but they talk about the accuracy of the predictability they have with their climate modeling. They talk about a 95 to 99% certainty of the likelihood of an event to occur. So that's the when you hear those percentages, it's not that that's a percent of scientists, that's the likelihood of that we're going to see this trend at the end of the 21st century. So potentially that's what you're maybe hearing. The other thing when it comes to the media and politics getting involved, I'm a scientist, and that's where I try and stick to my realm that I know really well. And unfortunately, it does involve politics because that's how public policy is informed, right? Scientists and the public inform public policy, and then those political leaders are the ones that inform the decisions going forward. But that's why we have a fair and balanced government with representatives from all of those sides. The media does still try and portray both sides of the argument, even like with vaccination and anti-vaccination. They often give equal time to both of those sides. But I would encourage everyone to go to the evidence. Find a scientist and talk to them about that evidence and say, back it up. Back it up with peer-reviewed publications and other scientists, interdisciplinary scientists that work with various fields like geology and biology, and chemistry and physics and oceanography, all of those things coming together. Find the evidence, because if it was like someone said, let's say we have some kind of disease process or cancer, and your physician says you need to do this kind of medication, this chemotherapy that's going to make you really sick. You're probably going to do some research on that chemo. You're going to ask questions and say, what is that going to do to me? Is there another alternative? You're going to go to the science when it's your personal health. Do the same, and don't just rely upon these sides that you're hearing from the media. So that would be my response. Yes, Brandon.
The most polarization of our country recently, especially with climate change and everything, has been largely due to the suspension of an act that I think is fairly not well known. It was called the FCC Fairness Act. It was called the Federal Communications Commission, and it meant to present an argument of both sides of interpretation. And what happened was it was suspended in 1987, obviously it was a close voting of 5-4 in the Supreme Court, and they said it was kind of like controlling the First Amendment rights. So the reason why there's been a push-polarization on both sides is because of it gave rise to the channels like Fox 4 News, or more leaning towards left and right liberals to a certain extent, and not opposing the sides that they used to.
Thank you.
Are there any other questions?
I have a comment.
Yes,
Tax Forward is going to have down in Brazil who is a well-known Democrat.
Fox 4?
Yes.
That's the local.
I would say, I'm not really too aware of the political party in Brazil, but I can already say the right president, the president of Brazil already has scandals going on.
This is a woman named Donna Brazil, and she's very active in politics and very much a leftist Democrat, and is joining channel to the Fox News Network. Oh, yes, she is.
Hi, Todd.
It's going to be interesting.
Well,
Mr. Love.
So is there going to be a push for, do you see a push for nuclear energy in the future? true in terms of?
In the United States, not necessarily.
Why
We
is
haven't
that?
had any nuclear power plants constructed in the United States since I think 1986. So I think, and we've had more that are being decommissioned. In other countries, France has growing nuclear capabilities because that's been their solution. It is a very clean form of energy production because there are no CO2 emissions to speak of, once that plant is already constructed. But kind of the writing's on the wall with the United States because we're just a little bit more skeptical about the potential implications. Yes, sir.
If you're interested in nuclear power, I recommend you look into thorium molten salt reactors. Some people are saying that might be the answer to all our troubles. I've heard that sort of thing before, but it doesn't have a lot of the problems that the type of nuclear power we have now, the fission power we have now. It might be, I don't know, I'm not an expert on thorium molten salt, but it might be a good idea.
I believe that we're actually entering in, or Japan, let me correct that, is entering into trying to deal with the situation at the Fukushima nuclear plants. And that's actually terrifying for the people of that area.
Once you've been faced with a disaster, they're very skittish about implementing. And they still have remarkable storage problems. We still don't have any solution for the spent nuclear fuel that we already have.
I think
It's stored on site, like in Glenrose.
Right, well, and wasn't the genuine idea originally they were going to shoot it into space? Thankfully, we didn't enter into that.
And then we'll send it to Nevada, Yucca Mountain.
Right, New Mexico, I believe, is the latest repository, as well as Texas. Seriously, they don't have a plan for where to store this, and it has a rather lengthy shelf life. I don't venture a guess, but I'm not sure we're accurately aware.
Only a couple million years.
Yes.
Actually, it's put us to sun.
Yes, sir.
Okay, so whether you and I disagree, or you and the professor in the back disagree, would you agree that technology is moving more towards renewable energy, like solar, or let's say maybe more like electronic Tesla vehicles?
Absolutely.
And with that said, if we move more towards that, wouldn't that be more like a free market approach where whether you and I disagree, whether man's happening or not, then you would actually get what you want?
Yeah, we all benefit from
Yeah.
that, absolutely.
The market-
And we reduce our dependence upon other countries. We also, reduce our dependence upon a known fuel source that is in limited supply. So we all win, I agree.
Jobs.
Yes, sir.
Sir, there's something you might want to look up. It's called winning the oil in game. If you Google that, there was a report published by Lovins et al. 2004 for the Defense Department that addressed these questions for profit and to make us energy independent and everything lovely again.
Winning the oil end game?
Yes, sir. Winning the oil end game. Lovins et al. 2004.
Thank you. Yes, sir.
There was this chart that you showed earlier, and it was the U.S., and I know you're talking about global warming and climate change, but the more darker and more red regions were heavily metropolitan areas. Obviously, we know it's like right around the Appalachian and the Rocky Mountains. So that being said, do you think there's a correlation between people confusing global warming and pollution?
Well,
Because like what I'm trying to
that's a
say,
good question.
if it is global warming or climate change, only those red parts producing the CO2, like you said, should be emitted kind of all over the globe, correct? And not just on those areas?
Right. They can be, they don't have to be an exclusive thing because CO2 has been identified now by the EPA as a pollutant. Even though directly it doesn't harm us, they've realized the impact that it has on the overall environment. So yes, in those industrialized areas, or the heavily populated areas, yes, they do produce more air pollution than the other areas. But they're measuring the temperature. Those pollutants in and of themselves don't increase the atmospheric temperature on Earth. But it is the gases, that may be a combination as part of those pollutants that are just the sole entities that are increasing that localized temperature. So.
Isn't it also with that density, you're right on point here, the population density is also showing a dramatic rise in asthmatics, especially children, but anyone with respiratory issues the numbers of bronchitis, asthma in children. If you look at those numbers, it's actually a little disturbing. But the more dense the population, Fort Worth is increasing, as a matter of fact. I don't have the figures on top of my head right now, but you can look this stuff up.
15th largest city, I think it's going to, if I'm looking into Austin, it actually probably will be the 10th largest city, surpassing St. Jude. Yeah.
So they are related to one another. Those pollutants are often emitted at the same time, but those pollutants don't have the same impact as those greenhouse gases.
Do you think people are confusing overpopulation and pollution with global warming?
People could, like the scientists, when you're saying people are confusing, or you're referring to just the general public?
So right now, like the mass media, almost everybody kind of refutes the chance of even a natural phenomenon where we will naturally warm or they're naturally cool. What I'm saying is, you see pictures of polar bears and melting ice caps and all that stuff, but is there like a difference? Like, oh, this is actually a natural phenomenon, or are people tying in the pollution and overpopulation that we're creating ourselves into pushing this agenda? Oh my God, the world.
There could be sometimes, I don't doubt, when there are people in order to push an agenda to try and push some propaganda that may pull those things together. Because, like for instance, you mentioned polar bears. With some of that, it may include both the pollution, because they have an accumulation of certain chemicals in their tissues that are reaching the Arctic, and they are faced with the shrinking ice sheets, for instance, in the Arctic.
One term we use for the heat island effect. Metropolitan areas got a lot of concrete, they generate a lot of heat. Keep the heat around for the sun. Put the heat from the sun into these cold heat islands. So use meteorology all the time. And for the asthma, they did a study, and it's been repeated a number of times. Children living in the country dealing with cattle and stuff like that have less asthma problems because they're exposed to microbes and their system develops the resistance. Where if they're in a town, they're not exposed.
Right. Back to the density issue.
Yeah, back to density.
In an agrarian lifestyle, yeah, you're absolutely right.
Yeah.
More fresh air.
Yeah,
So-
not just the fresh air, the microbes
Methane mixed in.
that they're used to from animals.
So back to your question, there's a possibility that people are conflating the two issues. But I think that's again where we have to look to the science to say that those are independent issues. They may correlate with one another, but the pollution issue and the greenhouse gas issue, those are two things. They may occur simultaneously, but those aren't the same thing.
I would say that in terms of environmental policies and what we have to be careful with is how fast we do our mitigation effect. If you do it too fast and too quick, you're going to see Bell vote for protest. You're going to see Bell protest with something.
It has to be in our economic best interest. If we say we're just going to shut down air travel, that's not feasible, right? It has to be feasible. We have to, the majority of us have to ascribe to this. It has to be something that's economically on our side.
All right, well, thank you very much for your questions, and thank you for Dr. Stamatis for a presentation.